Alrighty, folks, welcome to Chapter 13, the culmination of our trigonometry unit. There's a lot of really good topics and ideas in this chapter, so I'm really excited about it. The book, for my taste, does not emphasize a few points quite enough, so I am very excited in the upcoming videos to share with you some secrets about IB trigonometry. So let's jump in. This video, we're just going to look at sections A and B. So trig equations. For starters, you need to know when you've got to give up. This one here is going to be something that we're just going to want to graph and use technology, and it'll tell us what the solution is. You kind of have three pictures here. Obviously, we're talking about the TI-Nspire in this video series. So you graph your two functions. Basically, f1 is going to be this one, and then f2 is going to be that. We can see the line there. Y equals 4 minus x, and then the other 2 sine x minus cosine x is giving us some sort of a wave. But if it's paper 2, if you're allowed to use a calculator, then you should be, okay? And you're going to graph. You're not going to use nsolve. Okay, there is the nsolve function on the calculator, which is wonderful for like linear equations and stuff. But nsolve is only going to give you one of the solutions, and in this case, we see there are 3 solutions. So if you want to get all of them, you need to use the graphing method. Okay, so I just wanted to get that out there from the beginning. If you can use a calculator, you should use a calculator. But what about problems where we can't use a calculator? What are the techniques that we're going to use there? Okay, so here's a little note from the book. Since sine and cosine have all real numbers as their domain, that means that we could very often have an infinite number of solutions to an equation. That wasn't the case in this last one because this line is clearly only going to intersect it in 3 places. But had it been a horizontal line, for example, then that's going to have infinitely many solutions. Or had it been, instead of a line, had it been some sort of other, wavy thing, then that's going to have infinitely many solutions. So for this course, when we have trig equations, we're always going to have a fixed domain, a restricted domain, and that's going to leave us with only a finite number of solutions. Now, what that means is when we are solving the problems, we need to be very mindful of what that domain is. And the book doesn't really emphasize this point. They do it when you read through their example, but I don't think they make a big enough deal about it. So here it is. If we know, for example, in the problem that x lies in between 0 and 2 pi. Are you ready for this? I'm going to blow your mind. That means that, for example, 2x lies in between 0 and 4 pi. Is this amazing? Is this amazing? I could also say that 2 pi should be less than or equal to 2 pi plus x, which is less than or equal to 4 pi. All right, so this is all very obvious. Okay, I don't need to explain what's happening on the board here, but it might not be obvious to you to think about this in the context of a trig equation. Let me show you what I mean. So here's 3 trig equations. They all look fairly similar. They all have to do with sine. They all have equals -1/2 on the right-hand side. But notice that the input for that sine function is different. We've got x, then we've got 2x, and then we've got x minus pi over 6. And we've got a restricted domain here. X is in between 0 and 3 pi. So we're gonna use that, and we're gonna rewrite that domain restriction for each of these 2 in a minute. So first, let's just go through problem A, because problem A is easy. Sine of x is equal to -1/2. We could do this one in our heads right now. Okay, so I know that when it's pi over 6, for example, then the sine would be +1/2. Same thing is going to be for 5 pi over 6, which means if I want it to be -1/2, I've got 7 pi over 6, right, and 11 pi over 6. Those are my 2 values in the 3rd quadrant and in the 4th quadrant. I've been imagining my unit circle here. I've got 1 pi over 6, 5 pi over 6, 7 pi over 6, and 11 pi over 6. And those last two are going to have sign values of negative 1/2. Now that's going from all the way around the circle one time. So that's from 0 to 2 pi. My domain is actually up to 3 pi, so I'd continue going around here. But of course, sign is going to remain positive in the first two quadrants. So my only two answers for this first one should be 7 pi over 6 and 11 pi over 6. Let's see how the book represented that. Whoops, wrong way. Here we go. Okay, so same idea, right? Unit circle, they just wrote them down. So for this next problem, right, okay, so it's not going to be those same two numbers, 7 pi over 6 and 11 pi over 6. But we would start off the same way. We would kind of imagine that this said sine of x equals negative 1/2. If you prefer, some people might like doing this. You could write a new symbol like u. Let u equal to 2x. So then we'd start off by solving sine of u equals negative 1/2. And then we'd find out that u is equal to 7 pi over 6 or 11 pi over 6. And then we'd substitute back. Well, it's not u, really. It's 2x. So 2x is equal to each of those. And then that means that x should then be equal to 7 pi over 12 and 11 pi over 12. So that's one way to kind of approach this. Oh, I forgot to do the final answer for that first one. Anyway, for the second one, though, you'll notice now, wait a second, that's left out a whole bunch of answers. They've got 6 answers in theirs. We only have 2. So what happened there? Well, we're going to use the domain trick, and they've got it right here. Okay? They're not making a big deal about it. I'm making a big deal about it. Okay? So if x is in between 0 and 3 pi, then that means that 2x has to be in between 0 and 6 pi. So at this stage right here, we need to get more answers. U has to be in between 0 and 6 pi, not 0 and 3 pi. So we'd work out these additional values here. So we've got the first two, 7 pi over 6 and 11 pi over 6, and we just keep on going around the unit circle more times, right? We're going to go around it 3 times in this case, so to get to 6 pi. So on each rotation, we should be hitting 2 solutions in the third and fourth quadrants for a grand total of 6. So there they are. Okay, and then for letter C, we're going to do the exact same thing, right? If x is in between 0 and 3 pi, then that means that that x minus pi over 6 is going to be in between negative pi over 6 and 3 pi minus pi over 6. So let's do that here. All right. So when we're working this out, then all of a sudden we need to think not about going around the unit circle kind of like 3 more times. We're only maxing out at 17 pi over 6. And of course, as soon as we get to 12 pi over 6, which is 2 pi, there's not going to be anything else after that because we're only going to 17 pi over 6, which is right over here. Those are sign is going to be positive all there. So then we just need to think about working backwards. And negative pi over 6, that's the same as 11 pi over 6, so that they're going to have the same sign value, I should say. That becomes the third solution. All right, so that one's got 3. If that didn't make sense, I'm really sorry. I really hope it did. This is a big deal, though, when we're solving trig equations. If you don't want to miss solutions, you've really got to analyze it in this way by taking the original domain and then rewriting it so that instead of x in our inequality, we have whatever the input value was for the trig function. Okay, what if we have more than one trig function? Oh my gosh, what shall we do? So we need to start thinking about our identities. Okay, we've seen a few identities before. Okay, and I think the easiest one to deal with here is to note that if we divide both sides by cosine, then we're going to have root 3 times tangent of x should be equal to 1, and that actually becomes pretty convenient because then we can divide by the root 3, and then we've got this and this. That's something that we should know, right? Well, silly questions, thinking in degrees, but whatever. Yeah, we should know that that's going to be 30 degrees or 210 degrees. All right, that one wasn't too difficult. How about these? Ooh, can we find exact solutions of these? Back to the inverse functions now. Okay, so arctan of x is equal to pi over 3. So what we're going to do there is we're going to take the tangent of both sides. Right, so tangent of arctan of x, that should be equal to the tangent of pi over 3. We know that that's the square root of 3. For the second one, okay, we'll do the same thing. We're going to take the cosine on both sides. Right, so cosine of all that should be equal to cosine of that. Okay, that works equally well. We know the cosine of 2 pi over 3 is negative 1/2. So x minus 1 should equal negative 1/2. Okay, x is equal to 1/2. Great. What about this third one? Well, it's actually not doable. It's kind of weird, right? So what's going on here? So remember that we had to think about the ranges of the inverse trig functions in the previous video about that. So what's happening here, right? We can find the sine of 2 pi over 3, but we would never get 2 pi over 3 out from arcsine of x. Arcsine of x can only output things from negative pi over 2 to positive pi over 2. So this is actually an impossible solution. Or if that hurt your head a little bit, don't worry about it. You're not alone. I'm not a big fan of these either, but good news, not something that shows up too often. Anyway, that's it for section A. Again, the big thing here is using the domain trick, rewriting the domain of your normal trig functions so that you don't miss any solutions. So that's the most important thing in this video. And now we'll just talk section B really quickly. There's like a lot of things that you can model with trig functions, so just be aware that you could have a problem that looks something like this. This honestly, I don't know, this stuff is more seen, I think, at the SL level than HL, or be more likely to be seen there anyhow. But you know, let's look at it. All right, so we can model the tide in a given place by a trig function, right? Because the tide goes in and goes out, gets higher and lower, kind of like a trig wave, right? So here's the function that we're using for t in between 0 and 24, because that's hours after midnight. And okay, so we could graph it. This is a pretty easy one to graph, right? It's just going to be vertically stretched by a factor of 3. So we're going up from positive 3 to negative 3. And then it's going to have a period of 2 pi divided by pi over 6. 2 pi divided by pi over 6 is going to give us a period of 12. Which means, since we're talking about 24-hour period, right, that the cycle is going to repeat twice in that 24-hour period, which I guess makes sense in terms of tides. I don't know. I'm not an oceanographer, oceanologist. I don't even know what the word is to describe what I'm not. Anyhow, I digress. So we could graph that, and there it is. Okay, and we can analyze this. We can see exactly when, what the tide is at a few times. So noon is going to be down here when t is equal to 12, right? Since we're looking at hours after midnight. When is the tide the highest? Well, that seems to be at both 3 and at 15. 15, of course, is just 3 p.m. And that maximum height is going to be, well, it says it's 3. Now, what does that mean? What does that mean 3? Because if that's 3 meters, then this is what, negative 3 meters. That doesn't make any sense. No, but remember that this is the height above the mean sea level, so above the average sea level. So we can say 3 and negative 3, and it makes sense in context here. So whatever we don't know what the mean sea level is. So as far as what is this maximum height, it's just 3 meters above the mean. What's the height of the tide at 2 p.m.? Okay, well at 2 p.m. that's 14. That's whatever we get there. Okay, you could plug in 14 into your equation. I don't think anybody's going to know off the top of their head what sine of 14 pi over 6 is. Or will we? Hang on a second. 14 pi over 6. That's going to be that's the same as 7 pi over 3, and we should be able to work that out. Yes, absolutely. In fact, let's scroll down and see it. So, okay, they've changed it to a decimal there, but we should be able to do this, right? This is going to be 3 times sine of 7 pi over 3. So 7 pi over 3, well, let's see, this is 3 pi over 3, this is 6 pi over 3, so this is 7 pi over 3 is going to be up here. Okay, sine of 7 pi over 3 is the same as sine of 1 pi over 3, and sine of pi over 3 is going to be square root of 3 over 2. So you pump that into a calculator, and yeah, you're going to get 2.6 meters. Okay, great. And then the last question, I don't even remember what it was. A ship can cross as long as the tide is at least 2 meters above the mean sea level. So when can that happen? So we need to be at least 2. So we have a period of time here, and then we have a period of time here. And what we need to figure out, what are those exact values, right? We're basically going to set our trig function equal to 2 and then solve that. Right? So that's not the easiest thing to do. We're going to need the technology for this one. That's just not going to be possible without it. Anyway, these are our 4 times that we get. Again, we're not using nsolve. We're using the graphing screen, and we're actually going to find out what those points of intersection are. And then the final challenge for this one is 1.39. Remember that t is in terms of hours. So what is 0.39 hours? Well, it's about 23 minutes. So that would be 1.39 would be 1:23 in the morning. So from 1:23 to whatever this is. This is something a little bit past 4:30 in the morning. I don't know. Anyway, that's how we can solve this. That's trig modeling. It's pretty straightforward. I think you're going to know what you're doing with that. It's just solving some pretty basic word problems. Anyway, that's the end for this video. Once again, the big thing was the domain trick. Okay, rewriting the domain in terms of whatever the input values were for your sine. Next video, we're going to cover a whole bunch of identities and some more secret tricks in there as well. And then we'll close off this series with the last 2 sections. We'll do, look at that, quadratics. They're coming back. And, series as well. Get excited, folks.